general expression is Vt is equal to A1 into e to the power minus S1t plus A2 into e to the power minus S2t. For overdamped condition, this is the general expression.
Sir, it's minus or plus?
Which one?
E to the power minus S1 or plus S1?
Oh, sorry. Plus S1. Sorry. Yes. This is e to the power S1t and e to the power S2t. Right. So this is e to the power S1t and e to the power S. Sorry. This is S1t plus e to the power S2t. Okay. Now next you have to calculate S1 and S2. You have to calculate S1 and S2. So what is S1 and what is S2? This is, you know this. This is, what is S1 and S2? Minus alpha plus minus root over alpha square minus omega 0 square. So you just calculate this, what it will come. So this will come out to be, see, you will have two values, minus 2 and minus 50. You will have two values, minus 2 and minus 50. So S1 is minus 2, S2 is minus 50. Please calculate this. So your Vt you can write this as A1 e to the power minus 2t plus A2 e to the power minus 50t. See if this is okay or not. We have found out S1 and S2. Put the values of S1 and S2. Put the values of alpha and omega 0. You will find the two roots S1 and S2. Okay. Next, what you have to do? You have to calculate V0 and I0. You have to calculate V0 and I0, right? So what is V0? What is V0? Tell me. So if you put here t equals to 0, if you put here t equals to 0, this will become A1, this is 1 e to the power 0 plus A2 e to the power 0. That is, this is equal to A1 plus A2. And it has been given that this is equals to 5. So this is the first equation, that is A1 plus A2 is equal to 5. This is the first equation. Okay. Now next, you have to find out dv0 by dt, and this is equal to S1 A1 plus S2 A2 at dv0 0. So what was your initial expression? What was your initial expression when you had this parallel circuit? When you had this parallel circuit consisting of the resistance, and then you had the inductance here, and then you had the capacitance here. What was the initial expression? What was the initial expression? This was V by R plus 1 by L integration What was the expression? Do you remember what was the expression?
VD tau plus
EDC
I
plus
naught.
I naught
Correct.
plus
Plus C
CdV by dt.
dt. Right. So this was the initial expression. Plus C dV by dt. Let's, because your I0 is equal to 0. So if you just if you just consider this is the, let's say this is the initial current I0. We are just putting this entire thing as I0. Okay, because there is no initial other currents in the circuit. So if you just rewrite this, if you just rewrite the equation, so your equation becomes, that is dv by dt, this becomes equal to, this becomes equal to dv by dt is equal to minus, right, v by r plus I0, the entire thing divided by C. So this will be equal to minus V plus I0R, this is V0 divided by C. Okay, put the values of V0, I0, R and C, sorry, this will be RC, and this will be equal to your S1A1 plus S2A2. So you have these values of S1, you have the value of S2, you have the value of V0, I0 is 0. So this is just becoming minus 5 divided by 1.923 multiplied by 10 millifarad, that is 10 to the power minus 3. You are getting this, and this is equal to S1, that is minus 2A1 minus 50A2. So this is your equation number 2. Okay, so you are getting here two equations of A1 and A2. So you can calculate, solve A1, A2, solve A1 and A2, and you will get the expression of Vt. So Vt will be equals to A1 e to the power S1t plus A2 e to the power S2t. Solve for A1 and A2, you will get the expression of Vt. Clear? So this is for your first case. Now the second case, we are moving on to case 2. We are moving on to case 2. So what is case 2? What is R given in the case 2? R has been given as, let's just check out the, R has been given as 5 ohms. R has been given as 5 ohms. Okay, so in case 2, your R is given as 5 ohms. Okay, first part clear? So this is the second case. So what is alpha? Again you calculate alpha, 1 by 2 RC, that is 1 by 2 cross 5 cross 10 into 10 to the power minus 3, that is alpha is equal to 10. What is omega 0? Omega 0 is equal to 1 by root over LC, this will remain constant, and this is 10. So this is alpha is equal to omega 0. First you calculate this. So this is the critically damped condition. This is the critically damped case. So critically damped case, your S1 is equal to S2, and this will be equal to minus alpha, that is equal to minus 10. Right? Okay. So what will be your Vt? What is the expression of Vt? If you remember, the expression of Vt is, the general expression of Vt, this is a general expression I am writing for critically damped case. This is A1 a1 plus a2t into e to the power st. So here this will be a1 plus a2t into e to the power minus 10t. So if you just again calculate V0, your V0 will be equal to just A1. Your V0 will be equal to A1. Because see, if you put t equals to 0, so that is 0 and e to the power 0 is 1. So your V0 is equal to A1. So your V0 will be equal to, this will be equal to your 5. A1 is equal to 5. This is the critically damped case I'm talking about. Right? Okay. Again, what is dv0 by dt? What is dv0 by dt? Tell what is dv0 by dt. If you calculate this, or if you just uh, make dv0 by dt, so this will come out as, from this expression, this will come out as minus 10. Okay, just differentiate minus 10 a1 minus 10 a2t. Okay, and next is, so this will be uv formula plus a2 into e to the power minus 10t. Okay, so put v0, so at 0 this will be equals to minus 10 a1 plus a2, and this will be equal to your, which you have already got here, that is in the previous case you calculated dv0 by dt. Do you remember you calculated dv0 by dt in the previous case? Here this you calculated, this will be the same here as well, this will be the same. So this will be equal to minus v0 plus i0r by rc. So put the values here. You are again here, you know a1 5 as well. So you can write this as minus 50 plus a2 is equal to minus 5 by r, that is here your r is equal to 5 into c, it is 10 to the power minus 3. So you get a2 from here, and then you substitute the values in this general equation. Just put vt is equal to a1 plus a2t into e to the power st. So you put all the known values except t. This is your expression for vt. Clear? See, anybody is having any doubt, you can ask me. Because this
Sir,
yes,
sir, can you repeat this dv0 by dt part?
this one.
Yes,
Uh,
sir, the last part, dv0 by dt.
okay, sure. So you are talking about how did this come?
Yes, sir,
How?
yes, sir.
See, this is your vt was, what was your vt? Vt was this, right? So you separately differentiate dv. So this will be equals to d dt of a1 e to the power minus 10t plus d dt of d dt of, okay, I will do this separately. See, your v0 was a1 plus a2t into e to the power minus 10t. Okay, so we are doing dv0 by dt, that is ddt of a1 into e to the power minus 10t plus d by dt of a2t into e to the power minus 10t. So this is your, you remember the formula of d dt of uv, this one, this was your u dv dt plus v du dt. So we will apply this because you have two expressions of t here for this, and this will be simple. So for this you get, so from here for this you get simply minus 10 a1 into e to the power minus 10t, and for this you get minus 10 a2t into e to the power minus 10t plus a2 into e to the power minus 10t. If you are considering this as u and this as v. Okay, so you are getting this. So therefore if you take e to the power minus 10t common here, so you are left with minus 10a1 minus 10a2t plus a2 multiplied by e to the power minus 10t. Oh, this I've already written. So this, is this clear? We are just differentiating this.
Yes, sir.
Okay, so this is how we got this formula, that is this one, and then this was already known to you, so we have just put the values. You can calculate a2 from here. So this will be v0 is equal to a1 plus a2t into e to the power minus 10t. This problem's a bit lengthy problem. Okay, so we similarly we move on to the third case. So your third case is, what was your third case? Third case is your R was given as 6.25 ohms. Your R was given as 6.25 ohms. So similarly, we will calculate alpha and then the roots. Alpha and then the roots. So for 6 point, again we are putting 1 by 2 RC. If you put this at R is given as 6.25 ohms, you find your alpha is 8, sorry, your alpha is equal to 8, your omega 0 is equal to 10, so your alpha is less than omega 0. So this is an underdamped condition. This is your underdamped condition. Okay, this is the underdamped condition. So again what we will do, we will first calculate S1 and S2. We will first calculate S1 and S2, and you put the values of S1 and S2 as minus alpha plus minus root over alpha square minus omega 0 square, and you will find out what is the value of alpha. Find out what is the value of alpha, and you will see you get this as minus 8 plus minus j6 plus minus j6, minus 8 plus minus j6. Okay, so what was your general formula? You remember what was the general formula for underdamped condition? So this, we termed this as omega d. If you remember, I do not know. This we termed as omega d. Okay. So your formula was, your general equation was Vt is equal to e to the power minus alpha t. Your formula was Vt b1 into e to the power minus alpha t cos omega dt plus cos omega dt plus b2 into e to the power minus alpha t into sine omega dt. This was the general formula. So this is your alpha and this is your omega d. So what is your general formula coming out to be? So this is b1. This was the general formula if you remember. So they are coming out as b1 e to the power minus 8t cos 60 plus b2 e to the power minus 8t into sine 60. This is the general formula. Okay. Clear? So again the same method. What you will do, what you will calculate, first you calculate v0. So this expression becomes 0. This will become equal to 0 because sine 0 is 0 and cos 0 is 1. So you are left with b1 only. b1 e to the power 0 cos 0 plus b2 e to the power 0 sine 0. So this is 0. So you are left with only b1 and this is equal to 5. So you are left with b1 is equal to 5. Now you again differentiate this. You again for dv0 by dt, same thing. You have to do d dt of b1 e to the power minus 8t cos 60 plus d dt of b2 e to the power minus 8t sine 60. So if you differentiate this, if you separately differentiate this, see both are, this is your, for here this is your u, this is your v, here this is your u, this is your v. Correct? So here you are getting this as, let's say taking b1 constant, you will get minus 8 e to the power minus 8t cos 60 plus 6, or this should be minus 6 e to the power minus 8t sine 60 plus b2 into minus 8 e to the power minus 8t sine 60 plus 6 e to the power minus 8t cos 60. See if this differentiation is correct or not. Now you simply put you are calculating this at time 0. So this is d v0 at time 0 by dt. All the sign terms will be equal to 0. All the sign terms will be equal to 0. So this is 0, this is 0. So you are left with minus 8 b1 e to the power minus, so this is 0, minus 8 b1, this term is 0, and this will be again you are left with plus 6b2. So you are left with this, and this is equal to minus v0 plus I0 r upon rc. Understood? So from this you know the value of b1 as 5, you know the value of b1 as 5, v0 as 5, I0 as 0, R as 6.25, and C as 10 millihenry. Put the values, you will get the B2, and then put it in the general expression. Put it in the general expression. What was your general expression? A general expression. So you calculate. So your VT final will be B1 e to the power minus alpha t cos omega dt plus B2 e to the power minus alpha t sine omega dt. So here put the values of b1, b2, alpha and omega d. We will get the expression of vt. This is the condition for underdamped condition. See if this numerical is clear to you. This numerical clears all the, this is one numerical that I have given or that I have solved. This will help you to go through all the conditions or how to solve for your underdamped, critically damped or overdamped condition. Please see if there is any other doubt. If there is any other doubt, please see and let me know. Anybody? Anybody? You need to copy. I need to show you something. I think we can convert this into PDF and I can send you. But please just see if any questions. Bimbayon, Man, any questions? Is this clear, the method of solving this?
Yes, sir.
Okay. Priyanshu?
Yes, sir. Yes.
Okay.
Yes, sir.
So this is all the conditions I have shown you. Critically damped, underdamped and overdamped condition. Any questions anybody can ask me? Shumon, clear?
Yes, sir.
Shyoshi?
Sir, it's clear.
Okay. So then we move on to the, so this is about your natural response or free response in case of an RLC parallel circuit. So now we will move on to the next thing, that is forced response in case of an RLC parallel circuit. Then we will go to the series circuit. So let's first do the parallel forced response in parallel circuit. Then we will move on to the series circuit. Okay. Okay. So just a second. Just let me open the PDF. So next, what I am talking about is the step response. What I am talking about is the step response in case of the step response. So what is the step response? What is step response? Step response is nothing but you are having an additional source. You are having an additional source. So when I am talking about the parallel circuit, you know that the individual currents, of each of the branches gets adds up. So basically, why I am taking the current source, because this I, okay, this will be divided into this and this branch. So your I will be divided across IC, IL and IR. Okay, so that is why when I am talking about a step response of a parallel RLC circuit, I will concentrate on I. Now what happens if there's a V source? So let's say you have been given a V source and you have been given a parallel circuit. So what will you do? What will you do? Say you are given a V source. So
Potential is same across the branches.
no, you just do source transformation. Say you are given a voltage with a resistance here. Okay, you do source transformation. Yes, if no resistance is given, the voltage will be same across all the branches. So you calculate V by C, that is C dV by dt, 1 by L V integration V dt, and V0 R, you get the individual currents. But if it's a resistance given here in series with this voltage source, you first make the source transformation. So when it's a source transformation, so automatically you get here a current source, and in parallel to it you get a resistance here. You convert this resistance and this resistance, you combine these two resistances to get a single resistance, and then you can calculate it. So this is the method. So if it's a voltage source simply given, just calculate C dV by dt for current across a capacitor, 1 by L integration V dt for current across inductor, and V0 by R for current across the resistance. Or else, if it's a resistance given in series, you have to do source transformation. Okay, so from the KCL, that is from the KCL, you know, this already I wrote that your total I will be equals to IL plus IR plus IC. Okay, so what is, let's say you are keeping this current as IL. So your IR is V by R, and this is C dV by dt. This is integration. This is equal to I. Okay. Now what you have to do? What you have to do next? You know your V is equal to L di by dt. So what is dV by dt? dV by dt will be L d square I by dt square. So I am writing this expression. See, if you closely look at this, I am writing this entire expression in terms of IL. I am writing this expression in terms of IL. Please closely look at this. I am writing this entire expression in terms of IL. Okay? See, V was equal to L di by dt, right? So this expression becomes L by R dIL by dt. And your dV by dt was L d square IL by dt square. So this becomes LC d square IL by dt square. If you closely look at this, your expression was IL plus V by R plus C dV by dt. So this V is equal to L dIL by dt, and dV by dt is equal to L d square IL by dt square. So we have just replaced this here, and we are getting this expression of IL plus L by R dIL by dt plus ILC d square IL by dt square. So we have brought this in one common term. Now what we are doing, we are writing the second order equation. So we will divide everything by LC. We are writing the second order equation, that is dividing the entire equation by LC. So what you get? D square IL by dt square plus 1 by RC DIL by dt plus IL by LC is equal to I by LC. Clear? So basically you have
Sir, wait
two
a minute.
approaches, but okay,
Yeah, so stay there.
please note it down. Yes.
So after differentiating, we are dividing the equation by LC, na?
Yes. We are just keeping this. See, this is the second order equation. We have to keep this as d square IL, or else we cannot do that. We will not be able to do proceed further. So we have to do d square IL by dt square plus 1 by RC DIL by dt plus IL by LC is equal to capital I by LC. Okay.
Okay, sir. Okay.
Okay. So next. So basically you have two approaches, but I will tell you, you just go for this indirect approach. I will just say you go for this indirect approach. Do not think about the direct approach. That will be a bit confusing. You just have to do this indirect approach. So this was already known to you. Your IL was, this was your IL, this is the first equation, this was your IL, this was your IR, this was your IC. This is from the KCL. Okay. Now what we will do, we will differentiate once with respect to t. So if you are differentiating 1 with respect to c, this is getting v by l plus 1 by r dv by dt plus c d square v by dt square, and this was I was your constant. So this is coming out as 0. See, if you closely look at this, we have again found out an equation only with respect to v. We have found out an equation with respect to v. So d square v by dt square plus 1 by rc dv by dt plus v by lc equals to 0. So we are writing just the KVL equation, and then we are differentiating this. And next, to know the solutions of this, you can go on calculating after this. You know V0, you know I0, you know the characteristic equation, and you can go on calculating for the rest. Okay. Then what will be what will be IL? What will be IL? Tell me what will be IL? What did you get as IL? What did you get as IL? What was your IL? You know this characteristic equation, you can understand this. This is the characteristics equation from natural response itself. Now you have got here IL as, this was your expression. So you just put here IL L and you just can calculate this. See, IL is I plus A1 e to the power S1t plus A2 dash e to the power S2t. Nothing. It's just dv by dt. We are just doing this dv by dt. This is simple, I think. Okay. So this is your indirect approach. And what is your direct approach? You calculate IL0 and DIL0 by dt. I will show you from the formula itself. See, this is IL0 plus DIL0 by dt. So this is, you have to calculate IL0 and DIL0 by dt. Same thing. Just what you have to do, for natural response you did with V, for forced response you will do with a voltage source. For forced response you will do with a voltage source. See, I will just show you a problem, then you can understand it better. Okay. So I am talking about step response of a RLC parallel circuit. Just let me show you the problem. Just a second. Yes. See, just mark this. See, this is your general expression. Please remember this. This is your general expressions for overdamped condition, for critically damped condition, and for underdamped condition. What is IS? IS is your source current. Please look at these general expressions. I think this will be again easier like the natural response. See, here the formulas of alpha and omega 0, this will be same as natural response. Same as natural response. Okay, this is the general equation. This is the general equation for forced response. Okay, for forced response or step response. The forced response is also known as the step response. Please keep this in mind. If in your exam it comes as a step response, do not get confused. Step response, it will be same as the forced response. So see, the same equations, just you have the source current as extra. Have you seen the same expressions? Only the source currents are extra. And what you will do here, you have to calculate I0 and di0 by dt. I think you can note down these three equations. Please note down these three equations. For natural response, this was using V0. For forced response, this is using I. Only difference is this. Please note down the equations. Same equations, only you have the source current as addition. Okay. See, let's say this is the figure given. Okay. So this is your inductor. This is your resistance. This is your 8 millifarad is your capacitance. Okay. So first what we do, see, you have two voltages. Okay. So we will calculate the voltage across this 20 ohm resistance. Okay, I think this will be up. So this is your, the voltage is given as 30. Okay. So we will calculate the voltage across this 20 ohm and the voltage across this 20 ohm, or you can convert this into a current source. You can convert this into a current source, whichever is helpful for you. Or you can just simply calculate the voltage across this 20 ohm resistance. So if you calculate the voltage across this 20 ohm resistance, this is coming out as 20 by 20 plus 20 into 30 is equal to 30. Clear? Next, we calculate alpha. There are two resistors. So total R will be 20 parallel to 20. That is 10 ohm. So you put R is equal to 10 ohm. You see alpha is 6.25. Omega 0 is 2.5. Now you calculate S1 and 2. Okay. You calculate S1 and S2. Okay. So alpha greater than omega 0. So overdamped condition. So we will use this formula. We will use this formula, right? So what is IS? What is IS given as? IS is 4. IS is 4. And your I0 is also given as 4 ampere. I0 is also given as 4 ampere. Okay. So this becomes equal to A1 is equal to minus A2. See, any doubts you can ask me. Next we do di by dt. We calculate this. And what is di by dt? You can calculate this by L di0 by dt is equal to V0. From this formula, you can calculate what is di0 by dt. This formula I already showed you. L di by dt is equal to V0. What is your V0? V0 was 15 volt because it was there was some voltage drop across the 20 ohm resistance, and then the voltage was equal in all the branches. So the initial voltage was equal to 15 volt. So di0 by dt was equal to 15 by L, that is 15 by 20, that is 0.75. You calculate A2 from here and then you put this into the formula. Okay. Similarly, you can calculate Vt, that is LDI by dt. You can calculate IR from there. See, I think should I show you once again? I think there is some confusion amongst you. Hello?
Yes, sir.
Should I just explain it to you once again?
Yes, sir.
Okay. See, I will just show you. I will show you with the problem itself. Okay, see. So when I'm talking, so first things, I think this is clear to you that your okay. So I will just explain it to you once again. Just a second. Just let me go back to the whiteboard, then it will help you. Okay. So let's say I am talking about the forced response. Okay. So first, what you have to know that your VL or V, say V, is equal to L di by dt, and your d2V by dt2, this was equal to L di square by dt square. Okay, or d2I by dt square, the way we write d2I by dt square.
Is dv by dt or d2v by dt2?
d2V by dt2, ddt of dv by dt, ddt of dv by dt. Oh, sorry. Yes, you're correct. Yes, this is dv by dt. dv by dt is L d2I by dt2. Yes. Okay. So first, let's write the general equation. Okay. So your IT is equal to IS plus A1 e to the power S1t plus A2 into e to the power S2t. This is for overdamped condition. This is equal to IS plus A1 plus A2t into e to the power S2t for critically damped case. And this is equal to IS plus P1 cos omega dt plus B2 sin omega dt into e to the power alpha t, e to the power alpha t. Okay, e to the power minus alpha t, sorry, e to the power minus alpha t. So this is your general expression for undamped case. Okay. Okay. So what we will do, we will straight apply into these formulas. We will straight apply this into these formulas. Okay. Next, what is the problem given to you? See, here you have a current source of 4 ampere. Okay. What was the problem given to you? You are having a current source of 4 ampere, an inductor of 20 Henry, then you are having a switch here which is getting closed at t equals to 0. Then you are having a resistance here which is 20 ohm. Then you are having a capacitance here. The value of the capacitance is equal to 8 millifarad. And the voltage across this is equal to V. And then you are again having a resistance of 20 ohm, and you are having a voltage source of 30 volt. Okay. Now you see there will be some voltage drop across this. There will be a voltage drop across this. So what is the voltage drop? Your voltage drop will be equal to potential divider rule. So the voltage drop will be here, and you can calculate it across here. So what is the voltage drop? 20 by 20 plus 20 into 30. This is equal to 15 volt. Okay. So basically there is a voltage drop of 15 volt across this 20 ohm resistance. So what is the initial voltage across all this? So here also, in this branch also 15 volt, in this branch also 15 volt, in this branch also 15 volt. So you can write your V0 as equal to 15 volt, because you are having a voltage drop of 15 volt. So 30 minus 15 is 15 volt left. So your voltage drop is equal to 15 volt. So here the voltage across the capacitor, this is the voltage across the capacitor. Voltage across capacitor at t equals to 0. This is equal to 15 volt, right? Similarly, you look at this. This is getting closed at t equals to 0. So what is your inductor current at time 0? This is getting closed at t equals to 0. So before t, so at t less than 0, at t less than 0, no current will be flowing in this circuit. Only current, only I through inductor. So your I0 will be also equals to 4 ampere. This is the current through inductor. This much clear? This much clear?
Yeah.
Okay. Next, what is the equivalent resistance? 20 cross 20 by 20 plus 20. So this is equals to 10 ohm. You have two resistances in the circuits. Okay. Now you calculate alpha. That is 1 by 2 RC. You put the values of alpha, 1, 2 into 10 into what is your C? It is 8 into 10 to the power minus 3. Okay. You calculate what is alpha. See, alpha will come out to be 6.25. Alpha will come out to be 6.25. You calculate omega 0. 1 by root over LC. That is 1 by root over 20 into 8 into 10 to the power minus 3. So this will come out as 2.5. Okay. So alpha is coming out to be greater than omega 0. So this is the overdamped condition. Clear? What is the general formula of IT? This I have already written, IS plus A1 e to the power S1t plus A2 e to the power S2t. What is S1 S2? S1 S2 is minus alpha plus minus root over alpha square minus omega 0 square. So you can calculate S1 S2, and your S1 and S2 will come out to be, if you calculate this, S1 and S2 will come out to be C minus 11.978 and minus 0. This I am taking from the book itself, 11.978 and minus 0.528. Okay. So next what we have to do? We have to find out I0 and di0 by dt. So what was di0 by dt? Di0, see, initially you have already seen V was given as L di0 by dt. So what is di0 by dt? This will be given as V0 by L. V0 by L. What is V0? 15. What is L? 20. 20. So this you are getting as 0.75. And what is I0? I0 is equal to 4, right? So you just put this in the equations. You have IT as IS plus A1 e to the power S1t plus A2 into e to the power S2t. So what is I0? This will be equal to 4. What is the source current? Source current is also 4 plus A1 e to the power minus 11.978 t plus A2 into e to the power minus 0.528 t. So here I am putting t is equal to 0. So this is becoming 4 plus A1 plus A2. This 4. So this is becoming A1 is equal to minus A2. Okay. Next, what will be dit by dt? What will be dit by dt? This will be, this is a constant term. So this is becoming 0 plus S1 A1 e to the power S1t plus S2 into a to the power S2t. So this at di0 by dt, you are left with S1 A1 plus S2 A2, and this you have already got here, see, 0.75. So this is 0.75. So this is one equation. This is another equation. Put the values of S1, S2. A1 is equal to minus A2. Then you can calculate A1 and A2. Solve 1 and 2 to get A1 comma A2. So what is your expression? IT is equal to IS plus A1 e to the power S1t plus A2 e to the power S2t. So here this will be 4 plus, you know, the values of A1 e to the power S1 is minus 11.978 t plus A2 into e to the power minus 0.528 t. Just put the values of A1, A2, you will get the expression for I1, IT. See if now this is clear. Is this clear now?
Yes, sir.
Yes, sir.
Okay. So what you have to follow is the general expressions. I think this is the easier method to solve. You just focus on the general expression and then you can solve this. Right? Now next, if you are asked to calculate what is IR, what is IR? If you are asked to calculate what is IR, so let's say you have been asked to calculate what is IR. So what should be IR? VR by 20, or this should be, you can write this as VT by R. So what is VT? L you differentiate this, you get the value, and you can calculate IR. So you have to differentiate. So what is DI by DT? Now you differentiate this one. You differentiate this one. You differentiate this expression or DI by DT. Okay. And then you get L by R into DIT by DT. So this is how you calculate IR.
Can you just call up, sir?
Yes, sure.
Okay,
Tell
sir.
me
Wait.
where. So this is about the transients of an RLC parallel circuit. See, I would wait for you, plus, but please get yourself cleared about this. The transients of RLC parallel circuit.
Sir, scroll down, sir.
Yes.
Yeah, sir. Wait. Yes, sir. Done.
Okay, anybody any questions? Devobroto, Otonu, any questions? Kritika?
No, sir.
So is this clear? So this is about the force response and how you solve the numericals of force response. I have shown you with the overdamped condition. So the things will be same. So just remember what you have to do. You have to put this into the formula. You just learn the general equation. Once you get to the general equation, I think this will be very easy to solve. Okay, the numericals are a little lengthy, but not that tough. You have to just get what is I0, what is V0, if it's an overdamped case, if it's an underdamped case, and for you have to write that particular expression for the overdamped case or that particular expression for the underdamped case. So do not mix it up there. Otherwise, this is easy. So if you closely look at that, I said you at the very first day that if it's a source-free circuit, if it's a source-free circuit, if it's a natural response, you have only the transients. You remember? You have only the transients if it's a source-free circuit. Okay. So you see, when I'm talking about the source-free circuit, so what is the step? What is the steady state response? What is the source response? Okay. So when I'm talking about the natural response, this is the natural response. This is the step or forced response. Okay. So this is the overdamped condition. What is the overdamped ratio? Vt is a1 e to the power s1t plus a2 e to the power s2t. What is here? Here this will be it is equal to is plus a1 into e to the power s1t plus a to the power s2t. Right? Next is your critically damped case. So I'm just writing this. I think this will be helpful for you. A1 plus A2t into e to the power minus, you can write this as minus S1t, or you can write it also as minus alpha t, because what is for critically damped? S1 comma S2 is equal to minus alpha, so you can write this as well. So it will be again equal to is plus a1 plus a2t into e to the power minus alpha t. And for underdamped condition, Vt is equal to P1 cos omega dt plus B2 sin omega dt multiplied by e to the power minus alpha t. And your it is same as is plus P1 cos omega dt plus B2 into sin omega dt multiplied by e to the power minus alpha t. Okay, and these are common. Alpha is equal to 1 by 2 RC, omega 0 is equal to 1 by root LC, and omega d is equal to root over alpha square minus omega 0 square when alpha less than omega 0. And here also this is same, 1 by 2 RC, omega 0 is 1 by LC, and omega d is equal to root over alpha square minus omega 0 square when alpha less than omega 0. Okay. So see, if you closely look at this, the only difference is for natural response, we are writing this with Vt. For step or force response, we are writing this with IT. So this is for natural response. If you remember, this is completely your transient state. This is completely transient state. For step response, this is the steady state and this is the transient state. And for this is entirely the transient state. Similarly here also, this is the steady state, this is the transient state. Steady state, transient state. But for natural response, you only have the transient state. Okay, so this is just the general formulas that I have written down, and this is for RLC parallel circuit. RLC parallel. Okay. Okay. Any questions? I think you can apply this directly and you can calculate the formulas likely. Okay. This is RLC parallel circuit. And what will be the difference in the graphs? Can you tell me what will be the difference in the graphs? How will the graph look like? See, if just copy this down and let me know when you are done.
So means graph of which for overdamp, underdamp, critically
Yes, for
means what, sir?
overdamped, critically damped, and underdamped, and I'm talking about your under the conditions of forced response and natural response. Forced response and natural response. Yes. Just can you just try to do on your own, or I will show you the graph. Anybody? See, for the forced response, for the natural response, first let me do about the natural response. The natural response is the voltage is constantly getting, so this will be Vt, this will be T. Okay. So basically, okay, let's do this. Okay, just a minute. Just let me raise this. Okay. let's say this is your P and T curve. Okay. Okay. So if this is your so see this is your critically damped, this is your under damped, and this is your over damped. Okay, these are the curves. When I am talking about the current response, okay, so this is your over damped case, this is your under damped case, this one, this is your under damped case, and your this is your critically damped case. So this will just go up till this, and then it will settle down. This is the critically damped case. So see, please draw this on yourself, because drawing this curve here is becoming a little difficult. So I think you can understand this. So the over damped case is where the steady state response, or the before the time constant, it has almost reached the steady state condition. Over damped is where there are oscillations, and another is the critically damped case where it will go up to the transient state, and then it will settle down at the steady state after the elapsing of that particular time constant. So this is basically, you can say this is the time period, or tau. So this is the response of natural, and this is the response of forced. After this, so this is your transient state, this is your steady state. Okay, see, this has reached steady state far earlier. This is over damped, critically damped, and over damped condition. Okay, so these are the graphs. This is how the graphs look like. So next we will now talk about is the RLC series circuit, and we will talk about the natural response. Okay, see, anybody any doubt regarding RLC parallel, or we will move on to RLC series circuit? Any doubts, anywhere? You can ask me any doubts anywhere. Okay, and assume there is no doubts. So what we will do, we will talk about the series circuit. Okay, so what is the series circuit? How does the series circuit look like? How does the series circuit look like? So let's say the series circuit is like this. That is, you are having this is natural response, right? So when I am talking about the natural response, therefore there will be no, this is R, no voltage sources. So this is plus, this is minus, this is the capacitance. The initial voltage is V0 across this, and the initial current is I0 across the inductor. Okay, now and the same current I is flowing through the circuit. Okay, let's say the initial voltage is V0 across the capacitance, I0 is the current across the inductance, and let's say I is the current flowing through the loop. I is the current flowing through the loop. So basically your V of 0 is equal to V0, I of 0 is equal to your I0. Okay, now what we will do, same current is flowing, so we will apply KVL. So what is KVL? KVL is IR plus L di by dt plus 1 by C integration t equals to 0 to infinity I tau by dt. This will be equal to 0. Correct? Okay. So next what we are doing? What is the expression next? So we are eliminating the integral. We are eliminating this integral. So what is this becoming? We can write this as R di by dt plus L d2I by dt square plus I by C. This is equal to 0. So if you rewrite this, this will become d2I by dt square plus R by L di by dt plus I by LC. This is equals to 0. This is equals to 0. Right? Clear till now? Okay.
So what is the limit 1 by C?
T equals to 0 to infinity.
Okay.
Okay. And one more thing we can write from here is this. From here is R into I at 0 plus L d into I0 by dt plus, what is this? This is actually V0. This is actually V0. So this is V0 is equal to 0. So your di0 by dt, this will become equal to minus 1 by L minus 1 by L, okay, Ri0 plus V0. This is di0 by dt. Okay. Now, what is the expression? So what we will take here again, we will take I will be equals to a e to the power st, just as There we took v equals to a e to the power st. Here we are taking I is equal to a e to the power st. So if we are just putting this here in this expression, this will become a square a into e to the power st plus r by l into s into a e to the power st plus a e to the power s by lc. This is equal to 0. So this a e to the power st, we are taking this as common. So we are left with s square plus r by ls plus 1 by lc is equal to 0. Right? So this is your, this is the characteristic equation. Okay? If this is your characteristics equation, then what is s? Minus a plus minus, sorry, minus b plus minus root over b square minus 4ac by 2a, that is equal to minus r by l plus minus root over r square by l square minus 4 into 1 into 1 by lc by 2. So we are getting this as s is equal to minus r by 2l plus minus, if we include this entire thing, so this will be r square by 4l square minus 1 by lc. So here your alpha is equal to r by 2l and omega 0 is equal to 1 by root over lc. So this is the difference between series and parallel circuit. So Nipper frequency alpha is equal to r by 2l. Resonant frequency is omega 0, that is equals to 1 by root over LC. Okay, just get this clear first. Any questions? Any question? So this is for your, what was your Nipper frequency for parallel circuit? 1 by 2 RC. For series circuit, it is R by 2 RL. It is R by 2L. Sorry, R by 2L. For parallel, it was 1 by 2 RC. Here it is R by 2L. So this is the primary difference. This is the primary difference. Rest, I think this is as easy as the previous thing. As easy as the previous thing. Just do everything as reverse. Just do everything as reverse. So let's just write down the characteristics equation. Let's write down the characteristics equation. So if alpha is greater than omega 0, it's overdamped condition. And here your IT will be equal to a1 e to the power s1t plus a2 e to the power s2t. If alpha is equal to omega 0, its critically damped case, and this is IT is equal to A1 plus A2t into e to the power minus alpha t. And if alpha is less than omega 0, this is the underdamped case. This is IT is equal to B1 cos omega dt plus B2 sine omega dt into e to the power minus alpha t. What are the differences then? See, for parallel this was Vt, for series this has become It. And the only difference lies in the calculation of alpha. Only difference lies in the calculation of alpha. Alpha is equal to R by 2L. Rest you see, everything remains same. Just you have to keep in mind for series natural response, it is IT is equal to A1 e to the power S1t. And rest all are same. Omega D is equal to root over alpha square minus omega 0 square when alpha is less than omega 0. Alpha is less than omega 0. Okay, I think this is easy now. What you have to calculate or what you are given to derive is these things. You will be asked to derive these things. If derivation comes, it will come to derive these things, and then these are the general expressions. So you can just apply this directly in the numerical. If you are given the numerical, you see if it's an RLC series circuit or if it's an RLC parallel circuit, you calculate alpha, you calculate omega 0, you calculate S1 S2. S1 S2 is minus alpha plus minus root over alpha square minus omega 0 square. You calculate this and then just put in the general expression. So this is the natural response of the RLC series circuit. Rest you see, if you compare, you can compare on your own. You compare and see, everything is same as that of the parallel circuit. Only thing, your here the calculation of alpha will be different. Hence the calculation of S1 S2 will be different, and you get the expression for IT. You get the expression for IT. See, any doubts? Anybody, any doubts? Anybody? Auditrika, Bimbayon, this is clear?
Yes, sir.
What you have to remember is just this general formulas. And the general formulas follow the same pattern. You have to just remember which general formula, what will be the expression, what you will get to calculate. Is it IT? Is it VT? You just need to know that. Rest, everything is same. Okay? Just the difference is, so when I'm talking about the difference, just the difference between parallel and series is, for parallel, the difference between parallel and series is alpha is equal to 1 by 2 RC. Here alpha is equal to R by 2L. 1. For natural response, you get VT. For natural response, here you get IT. Why VT and why IT? Because in parallel voltage remains constant, for series current remains constant. So that is why VT and IT. For forced response, IT. Here for forced response you will get PT. Simple. This is the only difference that you are getting. Rest everything remains the same. Rest everything remains the same. So you are getting the that steady state. You are getting the transient state. Your expressions are same, and this expression is same everywhere. For critically damped, under damped, over damped, the expressions are same. Just you need to know what you are getting. So I think I have just I have briefed you this briefing of the entire thing. I think this will be helpful when you are applying these things for your gate problems. You can directly apply these formulas. You can directly apply this formula to calculate the expressions. You do not need to derive the things. You can directly apply this formula. See, you can go through Abhijit sir's book as well, but there this briefing will not be given to you. That is what I did. I have just briefed you. Now for your labs, when you were doing the labs, you got some values for voltage, current, over damped condition, under damped condition. So say when you are doing the lab, you are given any circuit, so you can calculate, or you would know that if it's an over damped circuit or a critically damped circuit or a under damped circuit. From there you will know the nature of the curve, or what type of curve you are going to get. You can calculate the S1 and S2, that is the two transient states or the transient times. And at any particular t, if you calculate t at any particular t, say t equals to 1 second, you put this in the formula and you can calculate if the graph has that value or not at that particular time from the formula. You can derive it from as well. Okay. See, is this is clear to you or not? Any problems, anybody? Otonu, Shreyoshi, Pritam, any doubts, anybody?
No, sir.
No, sir.
Okay. So I think this is the brief. This is about your series response, natural response. We will just complete with the forced response of series RLC circuit, and hence your second module on Thursday, and we will revise the numericals from network theorem on Friday. But I am still saying that this second order circuit is not there in your term one. Please focus on the first order circuits and your network theorems, KCL, KVL, all those things, start delta transformations, uh, combination of capacitors, the Thevenin's theorem, uh, again, Telegen's theorem. I have already said you there will be numericals from Thevenin's, Norton's, superposition, maximum power transfer. Okay, you will have problems from here, and you will have problems from KCL and KVL, say one problem each. You will have problem from start delta transformation, you will have problem from source transformation, and you will have problem from combination of capacitors. So you are having here, see, 9 problems out of, you can choose obviously to do out of that. And then you have problems from RL circuit, RC circuit, and switching of circuits. So lots of numerical options. You can go through those numerical options and you can do those numericals. I think the question paper is relatively easy. The question paper is relatively easy, that I can guarantee you. You have to just apply. The theoretical part is relatively easy. For the rest of the network theorems, that is your reciprocity theorem, Telegen's theorem, Millman's theorem. Just go through what the statement states. Okay. Or just the demonstration like I showed you for the reciprocity theorem. Okay, how many questions will be there? See, section A is comprising of 10 questions of 2 marks each. Section 2 will comprise of 9 questions, out of which you have to do 6 questions, 5 marks each. And section 3 will have 8 questions, out of that you have to do 5 questions of 10 marks each. So therefore you are going to answer total of 10 2 marks questions, 6 5 marks questions, and 5 10 marks questions. Okay. Okay. So we stop here today. We will have the next class on Thursday. We will complete with the transient stuff circuits. Then you have your exams in the next week. After that, we will begin with the third module, that is the AC circuits and the three-phase circuits. And then we will again come back to do the network theorems for the AC circuits. Okay. So let's stop here. I think everybody is present today. All 15 of you are present today. So I'm giving a present to everybody. So you can leave. If you do not have your questions, you can leave the class. Very theoretical, basic theoretical questions. Say, what do you mean by time constant? Or say, what do you mean by mesh and a loop? Or you say, state the KVL law. Like this, simple questions. 2 marks questions. Okay. Okay. If you do not have any questions, you can leave them.